Hey mathematics learners, welcome to Distance Learning with Lee, where I make learning mathematics super easy. So on today's video tutorial, we are going to be going through the grade 12 mathematical literacy paper 2 that was written in November 2023, right? And just like I basically, mentioned in the previous past paper, right? Before you even, start answering questions, it's very important. Okay, it's important that you have a look at the instructions and the information that is given to you, right? So we are basically told that this paper consists of 5 questions, okay? So you need to answer all the questions. Use the annexures in the addendum to answer the following questions. You need to use annexure A for question 2.3, annexure B for question 4.1, annexure C for question 4.2, and annexure D for question 5.3. You need to number the answers correctly according to the numbering system used in this question paper. Start each question on a new page. You may use an approved calculator. Okay, you need to show all calculations clearly. You need to round off all final answers, okay, appropriately. So that basically means that you must only round off the final answer, okay, unless stated otherwise. Okay, indicate units of measurements where applicable, right? Maps and diagrams are not drawn to scale unless stated otherwise. You need to write neatly and legibly. So here, what's very important, right? That's basically mentioned here. It says that you need to round off all final answers appropriately according to the given context. So when it comes to rounding off, we're going to follow the instructions that are given to us. If they don't give us any instructions, that means that we are just going to round off to 2 decimal places or 3 decimal places. All right, so I hope that's basically clear. So when you basically look at the first question, right? The first question basically deals with some theory questions, okay? It deals with us analyzing a strip chart, and it also deals with assembly, right? So these are the concepts that are basically, assessed in the first question. So let's basically have a look at question 1. It says the table below contains a list of explanations and definitions of concepts used in mathematical literacy. Table 1 is explanations and definitions of concepts, all right? So you've got A, B, C, D, E, F, and G, and we are basically given, an explanation or a definition of a concept, right? So so what's basically told us, right, is that we need to use table 1 above to write down the letter of the explanation or definition of each of the following concepts. So for me, right, what I basically advise my learners is that when you're basically going through these definitions, try to see if you can think of, a word or a concept that pops up in your head as you're basically, reading that definition or explanation, and just write it down there on the side before you have a look at, these terms or concepts that are given to us there, right? So that's basically, the advice that I, gave my learners. Okay, so let's have a look at the first one. So a drawing showing the streets for a person who drives a car. So if we have a drawing that shows streets for a person who drives a car, that sounds like it's maybe a road map or a street map. B, visual indication of a real life distance and its distance on the map. So for me, if we're talking about real life distance and distance on the map, I think that basically is a map scale. C, the boundary that surrounds a circular shaped object. Okay, if we're talking about a boundary or the outline of a circular shaped object, that seems like they're talking about a circumference. D, a position which roughly shows the location of an object. So maybe if we've got a position that roughly shows a location of an object in a map, right? A point, or I'm thinking a reference point would be a position that shows the location of an object. So I'm thinking here maybe that's a reference point. Okay. E, the sum of the areas of all the faces of a 3D shape. So if we're summing up the areas of all the faces of a 3D shape, that's a surface area or total surface area. F, the rate of covering a certain distance. So the rate in which a distance is covered, that sounds like speed. G, the amount of space that is enclosed by the perimeter of an object. So if we've got a perimeter of an object, the space that is enclosed within that perimeter is what? Area. Okay, so this is basically what you need to do fast, quickly. Okay, this shouldn't even take you more than like 5 minutes. Okay, and then now we can basically have a look at those words there and see which one best matches what we basically did there. All right, so question 1.1.1, a bar scale. So we saw here that an explanation that had to do with something about a map scale was what? It was B. 1.1.2, surface area. We already saw that. Okay, an explanation that talks about surface area was what? E. 1.1.3, a roadmap. We already saw that an explanation that spoke about a roadmap, street map was what? A. Question 1.1.4, we saw that an explanation that spoke about, okay, speed was what? F. Okay, so it's B, E, A, F, right? So that's basically, the tip there, right? Write down the words, the terms, the concepts that basically pop up in your head there first. And then once you've done that, try to see if you can match it with what you are able to think of in the table. Good. Now let's have a look at question 1.2. So with question 1.2, this is a strip chart. Okay, but this strip chart is not basically coming to us in a form that we basically used to. Why am I saying that? Remember, when we basically look at how we work with a strip chart, right? We know that if you want, to determine the distance between 2 points, right? If you want to determine the distance between 2 points, maybe from that point to that point, we would usually say maybe 980 minus 435 to get the distance between those 2 points. However, with this strip chart, that is not the case. Okay, so we're going to see why I'm basically saying that. Okay, so it basically says that Mr. Masunte stays at a guest house in Hearn Street. Below is a strip chart showing the streets he will use to reach his destination, right? So before we even have a look at the questions, it's very important that we give ourselves like 2 minutes, 1 minute, 3 minutes to just basically analyze the strip chart. What is actually happening there? Familiarize yourself with what is happening there. Once you've familiarized yourself with what is happening there, then have a look at the questions, okay, and see how you can best answer them. Okay, so what are the key features, okay, or that are given to us here? We are basically given a key here. It's very important that we do not neglect a key that is given to us, right? Okay, so the key basically says that if we see a dot and a distance, it indicates the distance between two consecutive markers. What does this mean? It basically means that if I'm going from this point there, if I'm going from this point there to that point there, the distance that I would have traveled from those 2 points is 980 meters. Okay. If I am moving from this point to that point, the distance that I would have traveled would be 435 meters. If I'm moving from that point to that point, the total distance that I would have traveled would be 870 meters. And if I am moving from this point to that final point, the total distance that I would have traveled would be 1,100 meters. So that is what's different when it comes to this strip chart compared to the previous strip charts that we are used to, okay? And what makes us aware of that is that key there. That key tells us how we need to basically deal with this strip chart, okay? So what else is happening here? We know that Mr. Mashunte, right, is basically traveling from the guest house, or stays in this guest house, and he's going to be going to this destination, right? So as he basically, moves from the Hearn Street to his destination, we can see that Mr. Hearn is going to pass, certain streets, okay? We can see that now here, right? This street here, this is called Hearn Street, okay? This street is Hearn Street. This street is Fraser. This street is Goring. This one is Austin, okay? And then this street is Winchester. This street is Oxford. This street is Iffley. This street is Regatta. This one is Marlow. This one is Newnham. This one is Eval. This one, Eynsham. This one is Cleve. This one is Chalgrove. And that is that. So it's important that we understand what's happening there, right? So the horizontal street there is Winchester. The horizontal street there is Hearn. Then this one there is Winchester. Then this one there is Iffley. Do you see there? Then this one there is Regatta. Okay. Then so we can basically see that with the horizontal streets, they basically put the horizontal names. They put the names horizontally like that. But with the vertical streets, they put the names vertically like that. Very important that we basically take note of that. I think now we're more than ready to have a look at the questions that are given to us. It says, write down how many streets Mr. Mashunde must cross before turning into Winchester Street. So how many streets is he basically going to cross before turning into, before he turns, okay, before he turns into Winchester. So how many streets is he going to cross? So that's basically where he is, that guest house. So he's going to pass Fraser, he's going to pass Goring, he's going to pass Aston, and then he's going to turn into Winchester. So how many streets must he cross before turning into Winchester? We can see that he must basically cross 3 streets. Question 1.2.2. Name the street that goes over the Klip River. So what's the name of the street that goes over the Klip River? So where's the Klip River here? We can see that this is our Klip River. So that's the Klip River there. Do you see there? So what's the name of the street that goes over that Klip River? So we can see that the name of the street that goes over the Klip River is, okay, from there to there, it's what? It's Iffley. Okay, so the name of the street is Iffley Street. Question 1.2.3. Calculate the total distance from the guest house to his destination, right? So we want to see from the guest house to his destination, what is the total distance? So I already discussed this with you, okay, on how we need to go about getting the total distance. Remember, the distance between the 2 points is indicated by those circular markers, right? So from there to there, we know that the distance is 980 meters. Then from there to there, the distance is 435 meters. Then from there to there, the distance is 870 meters. Then from there to there, we know the distance is 1,100 meters. So all that we want to do now, we want to add up all these values together to get the total distance from the guest house to his destination. So then the total distance will be equal to 980 meters plus 435 meters plus 870 meters plus 1,100 meters. We are going to punch these values into our calculator. You will get that the total distance is 3,385 meters. Done. Right. So let's have a look at the next question. So with the next question, it deals with assembling, right? Assembling is nice and easy. All that we need to be able to do when it comes to assembly, you just need to read your questions properly. Highlight the keywords so that you know what you are supposed to focus on, right? Look, so let's basically have a look at what is happening here, right? It says illustrated below are the steps and components needed to assemble a chair. Okay, the components to assemble the chair are labeled alphabetically, A to K, right? So we are basically told here, right? These are the steps to assemble a chair. We've got step number 1, 2, 3, 4, 5, and the completed chair looks like this. Then we've got the components needed to assemble the chair. So what's needed for us to put this chair together? We've got the chair back that's needed, the chair seat, mechanism, gas lift, chair base, chair arms, casters, screws. So we're going to basically see that we've got 3 different types of screws needed. A washer and an assembly tool will be needed called an Allen key, right? So we can see these are the steps that we need to follow, and these are the components that we are going to need to assemble this chair. Use the information above to answer the questions that follow. Determine how many types of screws are needed to assemble the different parts of the chair. So here, right, how many types of screws will be needed? Obviously here, right, you are not going to go now trying to count there by the steps. How many screws can you see? We are just going to go to the components needed to assemble. Then from there, we can see that how many screws will actually be needed to assemble this chair. We can already see that it's 1, 2, 3 screws. Done. Question 1.3.2 says use the steps to assemble the chair to identify the following. So here the question is telling us where we need to focus our attention. We need to focus our attention on the steps to assemble a chair. Okay. A, the letter that indicates the chair base. So we want to basically have a look at the steps to assemble a chair, and we want to see what letter is used to indicate the chair base. What letter is used to indicate the chair base? We can already see from the components needed that our chair base looks like this, né? So that basically means that from the steps, we're going to look for a figure that looks like that. So we can see that it's this figure there. So what letter is used to indicate the chair base? We can see that the letter that is used to indicate the chair base is what? F. B. Use the steps to assemble a chair to identify the following. The number of screws used in step 4. So now we are still focusing on what? The steps to assemble a chair. And from the steps, we want to see the number of screws that are used in step number 4. So how many screws can we see in step number 4 were actually used? So you can see that there, right? The number of screws that are actually used in step number 4, it's 1, it's 2, it's 3, it's 4. We can see those are screws because it's indicating to us that these components must be drilled in like that. So you can see with those dashed lines there that is actually also indicating that those screws must go into those holes there. So we can see that how many screws will be actually needed or used in step number 4? 4 screws. Question 1.3.3, name the tool needed to assemble a chair. So now we're not focusing on the steps to assemble a chair anymore, right? We are basically now looking at just the components, right? So what's the tool that will be needed to assemble a chair? The only tool that is indicated to us here, or the only component that talks about a tool is what? The Allen key. So that is the tool that will be needed. Question 1.3.4, identify the component. So that means that we're focusing on the component of the chair that comes as a pair. So we're going to look at the components and we are just going to try and identify which components here comes as a pair, comes in twos, right? So which component can we see there comes in twos? It's the chair arms. And that is basically it. right? We've basically completed the whole of question 1 that basically dealt with what? It basically dealt with us, some theory questions there. We had to basically draw on the theory, okay, certain things that we've learned throughout mathematical literacy when it comes to measurements, when it comes to maps and plans, right? Okay, and we also had to basically analyze the strip charts, and then we also had to tackle assembly, right? So we're going to have now a look at our next questions. Question number 2. So question number 2 basically deals with, a layout plan. We're going to be analyzing a layout plan, right? We are going to be, calculating packaging, right? So we're going to be determining how many, boxes of bottles can be placed on, this table, and we are also going to be analyzing a roadmap. So let's basically have a look at what is basically happening here, right? So question 2, okay, shown below is the layout plan of a conference room in the Pretoria Hotel, right? So we know that if we are dealing with a layout plan is a top view of a building or a structure, right? That is what we are talking about if we are talking about a layout plan. However, if we are talking about an elevation plan, right, an elevation plan is a side view of a building or a structure, right? So you are supposed to know the difference between the two, right? So here we are just given a layout plan, which is a top view of, this conference room in the Pretoria Hotel, right? Before we even have a look at the questions that are given to us, it's very important that we first give ourselves a minute to analyze what is actually happening in this layout plan. So what is happening here, right? So we can see here, right, that okay, here we've got, some windows on, this layout plan. We've got a door, right? There's a refreshment table, right? And there are also key features that are given to us on this layout plan that are going to help us better interpret, right, what is happening here, right? What do I mean by this? We are given a compass there, and we are also given a key, right? So from the key, what we can see that if we see these symbols, those basically mean that those are just chairs, right? If we see the symbol, this basically means that those are plants, right? And if we see this symbol there, it's basically the screen for presentations, okay? So what are we supposed to do with this compass that is given to us here? Remember, I always give you guys this tip, right? If we're given a compass, you need to first start off by just filling in the other cardinal points, right? So already here we are told that the north is downwards like that. So we need to fill in the other cardinal points. And how are we supposed to fill in these cardinal points? Remember, I always say that you need to move in a clockwise direction when you're basically filling in these cardinal points. So what do I mean? If we're moving in a clockwise direction, we are moving in that direction. So that means that when we're filling in these cardinal points, we need to fill them in going in that direction. So if we're already there, that's our north. That means that to fill in our east, we need to go from there. To fill in our south, it's there. And then our west is there. So remember, naughty elephant sprays water. So I've filled in the other cardinal points, moving in a clockwise direction. Very, very important. Okay, so it basically says that now, all right, use the information above to answer the questions that follow. So we've analyzed this layout plan. We've basically filled in our cardinal points. We know what our key means. We're more than ready to answer the questions. What does the term layout plan mean? Remember, I've already given us this definition. When we are looking at a layout plan, right? A layout plan basically means that it's a top view of a building or a structure. Okay, so a layout plan is a top view of a building, and this top view of a building or structure basically shows us how, items are arranged in a room. Okay, and we are basically done. Question 2.1.2. Write down the total number of chairs around the oval shaped table. So we can see that this is our oval shaped table. So how many chairs do we have around this table? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 chairs around this oval shaped table. Okay, 20 chairs. Question 2.1.3. Write which one of the following statements regarding the conference room layout is true. So we basically need to read now these statements and we need to identify which statement is true. A, the screen is on the eastern side of the room. So let's see. Is the screen on the eastern side of the room? We can see that the screen is not on the eastern side of the room. The screen is actually on the western side of the room. So we can see that this statement is false. B, the screen covers some windows. Let's look here. Does the screen cover any windows? No, the screen does not cover any windows because we can see that the windows are on this side. Okay, so we can see that this statement is also false. And C, the screen is opposite the door leading into the room. So let's see, we can see that the screen is in fact opposite to the door leading into the room. Therefore, we can basically conclude now that this statement is true. So which one of the following statements regarding the conference room layout is true? So for question 2.1.3, which statement is true? It's C. Okay, good. Question 2.1.4, give one possible reason why plants are not placed on the table on the northern side of the room. Why are plants not placed on the table on the northern side of the room? So where's the northern side of the room? So we can see that the northern side of the room is this side, okay, because this is where our north is. So the northern side of the room is anything that's on that side. So why have they not put any plants on top of this table? Why didn't they do that? Okay, they didn't put any plants on top of this table because we see that if they were to put plants there on top of this table, those plants would actually obstruct, the view of the participants that are actually sitting on these chairs. Okay, so that's basically the reason why the plants are not placed on the table on the northern side of the room. Okay, the plants would just obstruct the views of the participants. Okay, the plants would obstruct the view of the participants that are actually sitting on the northern side of the room. Good. Okay, question 2.1.5, the actual outside length of the conference room is 12 meters. Right, so here we are basically told that the outside length of the conference room is 12 meters. Okay, so if they're talking about length, what would be the length? What would be the width? Okay, so let's just quickly focus on that for 2 seconds. Remember, right, the length is the longer dimension, right? So if you basically have a look at, this conference room, we can see that the longer dimension is this one. So that means that this is the length of our conference room and this is the width of our conference room. So this would be the width of our conference room and this would be the length of our conference room. We are told that the length of our conference room, okay, the actual length, the real life length is 12 meters. A, we are told to measure the outside length of the conference room on the layout plan. So remember, when you're given these types of questions, you just need to remember that you just need to take out your ruler and you basically need to measure the length from there to there with your ruler and give what that dimension is. right? So if you basically have the physical paper and you've printed out this layout plan on, an A4 piece of paper, if you measure with your ruler from there to there, I'm just using my digital ruler so that you just see what we're supposed to do, right? So you're gonna just put your ruler nicely there. Then when you measure, so from our digital ruler, we can see that the length is actually equal to 14.123. It's 14.3 centimeters. So that's just basically, the length that I get in centimeters if I'm using my digital ruler. But if you've printed out this paper and you actually measure, the length of, this conference room, you are supposed to get approximately 12.7 centimeters, right? If you're measuring in centimeters, or you're supposed to get 127 millimeters. Okay, remember, you can measure in centimeters or in millimeters, it doesn't matter, provided that they basically didn't tell us which units to use. They didn't tell us to use centimeters or millimeters, so that means that you can choose which units you want to measure in, right? So I'm just going to use the units in centimeters. So 2.1.5. What is the measured length of the conference room on the layout plan? So the measured length is equal to, I said I'm going to use centimeters, so it's 12.7 centimeters. Okay. And question number B, hence calculate the scale used in this layout plan. Now they actually want you to create the scale for this layout plan, right? So obviously you won't create a bar scale, okay? You won't create a line scale. We are going to create a number scale. How can we go about creating a number scale? Now here you basically need to remember, right? With a number scale, or when you're working with a scale, right? The scale basically tells us that the distance on the map is equal to distance in real life. Okay, so the distance on the map is to distance in real life, right? So now we're gonna basically take, the dimension that was given to us there of 12 meters. That 12 meters was the real length of the conference room, 12 meters. Okay, the measured length of the conference room was 12.7 centimeters, and we are going to basically substitute those values and just put them on this ratio scale, right? Okay, that's the first thing that we're going to do. So which value represents the map or the measured length on the map on the paper? It's 12.7 centimeters. Is to which value represents the real length or the length of the conference room in real life? It's that 12 meters. Good. Now, what's the next thing that we need to do? We know that when we are dealing with your number scale, right? Think back to how a number scale looks, right? When you obviously analyzing a map, how does a number scale look? An example, e.g., of a number scale is 1:500. That is an example of a number scale. 1:50,000. That is an example of a number scale. So that basically tells us that to convert this scale into a proper number scale, we want to get to a point where we've got 1:something. How can we get to that point where we have 1:something? We can already see that we've got a problem here. Our units of measurement are not the same. We've got centimeters on the left, we've got meters on the right. So that basically means that we first need to convert these units and make them the same. Once our units are the same, then we can get to that point where we can now divide by the value on the left to get 1:something. Let's take it away. So I'm going to basically choose to convert meters into centimeters. Please note here, even if you choose to convert these centimeters into meters, we are going to get the same answer, right? So I'm just going to choose to convert the meters into centimeters. So I'm going to leave this as 12.7 centimeters is to, I'm going to convert these 12 meters into centimeters. So now this is where now you need to know how to convert. When it comes to measurements, you need to be able to convert. Conversion is very important. You need to be able to know how to move between the different units of measurements for length, for volume, for weight. So how can I convert meters to centimeters? You need to make use of that diagram that I always use in my channel, okay? How can you move from meters to centimeters? If I want to move from meters and I want to go to centimeters, I need to I need to multiply by 100. So I'm just going to take that 12 meters multiplied by 100. What do I get? So then whatever value that I'll get, it'll be in centimeters. So now I've got 12.7 centimeters is to 1200. So 1,200 centimeters. So now that my units are the same, I can now divide by 12.7 centimeters on the left and divide by 12.7 on the right. So 12.7 divided by 12.7 centimeters, 12.7 centimeters, because I want to just have 1. So 12.7 centimeters divided by 12.7 centimeters gives us 1 is to 1,200 divided by 12.7 is equal to 94.49. Okay, the centimeters and centimeters have cancelled. We do not have any units there. Okay, please note that here I've just rounded off my answer to 2 decimal places. They haven't specified how I need to round off. So if they haven't specified, that basically means that I'm just going to round off my final answer to 2 decimal places. Okay, I hope that makes sense. So we've now basically changed or created a number scale based on the information that is given to us on the real distance and the measured distance. Okay, so I hope that basically makes sense. Right, let's have a look at the next question. Question 2.2. Now, question 2.2 deals with packaging, right? It deals with packaging in 2D, okay? Because we're just looking at just the top view of this table, right? So we want to determine what's the maximum amount of packed water bottles can I place on this rectangular table, right? So let's see how we need to go about tackling this problem. A single layer of the water of the bottled water will be packed on a rectangular base. The packed bottled water will occupy half of the length of the rectangular refreshment table. Very important here. We told something, okay? They're just telling us that the packed water bottle will only occupy half of the length of the rectangular refreshment table and will not overlap the edges of the table. Shown below are the pictures and the dimensions of the top of the rectangular refreshment table and the packed bottled water. So these are the dimensions of the rectangular refreshments table. We've got the width, which is 49 centimeters. We know the width is the shorter side. So that's our width. Our width is equal to 49 centimeters. Okay, and we are told that our length is 290 centimeters. So the distance from there to there is 290 centimeters. Okay, then we're given the packed bottled water dimensions, the width, okay, for this packed water. So there, from there to there, the width is equal to 24.2 centimeters. And we are told that the length, so from there to there, the length is equal to 36.4 centimeters. Calculate the maximum number of bottled water that can fit on this half of the table. What's the maximum number of packed water bottles? Okay, how many packed water bottles can we actually fit on this half table? Okay, so now remember, we are told that, okay, these bottles will only occupy half of the length. So if they're only going to occupy half of the length, what does that mean? It basically means that we need to half this length of 290 centimeters. When we half the length of 290 centimeters, how much are we getting? We're getting 145. So it means that we are just going to pack the bottles from there to there. Okay, we are just going to pack them from there to there. So the length that these bottles are actually going to occupy is a length of 145 centimeters and a width of 49 centimeters. So now we know when we are dealing with packaging, we are just trying to determine how many bottles can we fit along the length, how many bottles can we fit along the width. That is what we normally do. That is how we normally approach this question. So now let's see, right? Let's put that into context. So the bottles that we can fit along the width. So this is question 2.2. Okay, so we're just going to say bottles or packed bottles along length. That's the first thing that we want to start off with, right? So how many bottles can we fit along the length of this table, right? We're going to take the length of this table, which is 145 centimeters, and we're going to divide by the length of these bottles, right? So here, what we're basically trying to determine, this is my table here. This is just the top view of my table. Okay, this is just half of my table. Let me actually do it like this. I'm actually going to show you guys this half. This is my table, right? Remember, I just want to work with half of my table. So I'm just working with this half only, okay? And I'm trying to determine how many packed water bottles can I actually fit along this length of 145 centimeters, and how many packed water bottles can I fit along the width of 49 centimeters. So what we're trying to do, we're trying to determine how many bottles can I fit there along this length. How many can I fit along this length? That's what we're trying to determine. Is it 3? Is it 2? Is it 1? That is what we are trying to determine, okay? So to determine that, what are we going to do? We are just going to take the length of that table, the half length of that table, which is 145 centimeters, divided by, obviously, it's length to length, né? Length to length, width to width. So what's the length of the packed water bottles? The length of the packed water bottles, right, is 36.4. So 36.4 centimeters. Okay, so how many packed water bottles can we fit along the length? So 145 divided by 36.4, we see that we can actually fit how many? 3.983516,484. Okay, but remember, okay, we are not going to say we can fit 3.98 bottles. That doesn't make sense because they told us that there mustn't be an overlap, right? So what does this mean? It basically means that we can only fit approximately 3 packed bottles along the length. Okay, so that means along this length, I can only fit 1, 2, 3 packed water bottles, right? Because that 0.98 just basically means that means we have to cut this bottle in half there, right? There will be an overlap there, right? That 0.98 means that, I mean, if I had to now try to force in the fourth one, the fourth packed water bottle, there'll be an overlap there. And they told us that they don't want any overlap. So the maximum that I can just fit the whole bottles, packed water bottles that I can actually fit there is just 3. Okay, just round it down. Also, even when you're just looking at, like, a box that is, and you're trying to determine how many items you can fit inside the box, you always just now go a value down, because if you go up, then that basically means that you're saying that I need to cut, you need to, if you go up, there won't be space. If you go up, there won't be space. So that's why we basically round down. Even in a box situation, the maximum that I can fit even in this box for these packed water bottles to sit properly and to fit, it's 3. But in this table, okay, we can actually, put 4. But because they told us that there mustn't be an overlap, it's just going to be 3. Let's continue. How many packed bottles can we fit along the width? So the packed bottles along width, what do? We basically going to be working with width of the table, width of the bottles, right? So what's the width of the table? It's always the bigger width at the top. So you're going to take that 49 centimeters divided by, what's the width of the packed water bottles? It's 24.2 centimeters. So if you take 49 and you divide it by 24.2, how much do you get? You see that, okay, it's 2.02479388, meaning that we can just only fit 2 packed water bottles along the width, right? So let me just now change this drawing. Okay, so we found that along the length we can fit 3, 1, 2, 3, and then obviously there's going to be a bit of space left, right? And then along the width we've just calculated that we can just fit 2. Okay, right? That's what we've calculated. So what does this mean? Along the width I can fit 2, along the length I can fit 3. So what's the total amount of packed water bottles that I can fit into this table? So the total packed water bottles will be this 3 multiplied by that 2. Because do you see that we haven't finished packing there, right? We just filled in the 3 there. So we still need to complete the placing of these packed water bottles, right? So 3 multiplied by 2 gives us 6 packed water bottles. So what does this mean? We can fit 6. So 3 along the length, 2 along the width. In total, I can fit how many? 6. But then now, right, they said, what's the maximum? So we need to now try and see, right, is there any space, right, that is left on this table where I can squeeze in another bottle, a packed water bottle? How can I determine that? If there'll be any space, because I want to see, can I squeeze in these packed water bottles maybe in that way instead of just packing them like this? Maybe I can pack them like that. Can I do that, right? Because they said, what's the maximum amount of packed water bottles that we can fit? Okay, if they didn't put it that there, we're just going to leave it at 6. Okay, but we want to determine what's the maximum. Is there a packed water bottle that I can squeeze in there, right? So what's going to help us determine that? So remember, we found that the length of this packed water bottle from there to there, the length was given to us as 36.4. The length is 36.4. So from there to there is 36.4. From there to there, it's 36.4. 36.4. From there to, it's centimeters. From there to there, it's 36.4. So I want to see how much space did I use along the length. How much space did I use along the length? So if we take 36.4, you multiply by 3, how much do you get? You see that, okay, along this length, right, I've actually used 109.2 centimeters, right? So I've basically taken that 36.4. So the space used along the length, I just took the 36.4 centimeters, multiply that by 3, and I'm getting 109.2 centimeters, right? Okay, so that means that I now want to determine how much space do I have left there. What is that space that I've left there? That space there. What is that space there? There. Do you see that space? How much space is left there? So to determine how much space is left there, so the space left, I'm just going to take the 145 centimeters and I'm going to minus 109 centimeters. So 145 minus 109, I'm getting 36 centimeters. So that means that I still have space of about 36 centimeters there. I'm going to write that down. 36 centimeters there. Now let's think about that for a second. If I've got space of about 36 centimeters left there, that means that maybe I can pack, instead of packing, these packed water bottles like that, I can pack it like that, right? So I can pack it like that. But now all that I need to determine now is what's the length there? What's the length there? Okay, remember, if I've got 36 there, that means that, okay, I can pack at least one packed water bottle along, its width. And then, will I be able to fit the length there? Definitely, I'll be able to fit the length there because the width there is 49 and the length of this packed water bottle is 36.4. So that means that I can actually fit one more bottle into that space there. Do you see that? I can fit one more because that's 36. This is the width there. Okay, I've got the width of the packed water bottle is 24.2 centimeters, but I've got 36 there. I can fit it in there, right? And then the length of 36.4. So I can fit one more packed water bottle in that space. So what does this mean? Therefore, we can conclude, therefore, the total that I can fit will just be the 6 plus 1, which is 7 packed water bottles. Okay, something a bit interesting there. Very interesting. Requires us to think. What would be the maximum? Okay, if they didn't put the maximum there, we're just going to stop at 6. But because they put the maximum there, we want to maximize the amount of, packed water bottles that we can actually fit into that table. So you need to think along these lines. Okay, good. And we are basically done. Let's have a look at question 2.3. On Annexure A is a roadmap and area information directing the conference attendees to the Pretoria Hotel. Use Annexure A to answer the questions that follow. So here, we need to make use of Annexure A. That's my Annexure A, okay? So that's basically our Annexure A. And we're going to now, before we even look at the questions, okay? Before we even look at the questions, we are just going to analyze this Annexure, right? So this is obviously a roadmap, right? So if we're given a map, any kind of a map, you want to look, is there a key? Is there a compass? Are we given a map scale? Okay, that's basically what we need to look out for when we are analyzing our maps. So if we have a look at this map, right, we can see that definitely we are given a key, okay? We are given a key there that shows us what all the different symbols on this road map mean. This dot is a traffic light. ST means street. N is north. N and a number is the national roads. INT means international. Then we've got that N there. That N is our compass. Remember, if we see the compass there, we need to fill in the other cardinal points. So if our north is facing the left, that's our north. They're just saying that the north is facing the left. So how do we fill in the other cardinal points? Remember, we move in a clockwise direction to fill in the other cardinal points. So it's going to be naughty. Elephant sprays water. We filled in the other cardinal points. This is going to be very important, most especially if they're going to ask us for general direction, clear set of direction. We will have to use this compass there. So it's very important that we also just put it there for us so that it's ready for when we want to use it. Right? Anything else that we're seeing there? Pretoria Hotel, symbol 193, meaning that if we see that symbol 193, that basically means that that is Pretoria Hotel. What else are we seeing here on this map? We can see that all of these routes on this map, right? We are given 1, 2, 3, 4, 5. So let's see. From 1, if you follow this route, you follow, it leads to Pretoria Hotel. Number 2, you follow the arrows, it leads to Pretoria Hotel. 3 leads to Pretoria Hotel. 4 leads to Pretoria Hotel. 5 leads to, if we are following the arrows, Pretoria Hotel. So all 7 leads to Pretoria. All of these routes that are indicated by all these different numbers lead to Pretoria Hotel, right? So now I think we're ready to have a look at the questions, okay? Use Annexure A to answer the questions that follow. State the general direction of the Atterbury Road off-ramp from Fountain Circle. Remember, the key here is that if you're asked to give the general direction, the word after from is where we are starting. So in this case, they're saying from Fountain Circle. We are starting at Fountain Circle. We are going to Atterbury Road off-ramp. We are starting from Fountain Circle. That's Fountain Circle. That's where we are starting. We are going to Atterbury off-ramp. Atterbury Road off-ramp is somewhere there. So what is that general direction? From that point to that point. What is the general direction? Okay, you can already see it's the roughly southeast. Do you see there? Southeast direction. Okay. Also, then another tip, maybe you can just draw your compass on that point where you're starting from, right? So if you draw your compass on that point where you're starting from, it basically means that now this is my compass, that's my north. Remember, my north is facing in that way. Okay. So if that's my north, that's my east, that's my south, that's my west. Do you see that this red line is in between south and east? So the general direction from Fountain Circle to Atterbury Road off-ramp is southeast. Okay, I'm going to answer these questions here. Running out of space. Question 2.3.1. Okay, question 2.3.1. We said it southeast. Good. Question 2.3.2. Explain the phrase map is not drawn to scale. If they tell us that this map is not drawn to scale, right? If you have a look at there, right? They're telling us that the map is not drawn to scale. What does that mean? It basically means that there is no correlation between the measured length on the map to the actual length in real life. That is what is meant when they say that the map is not drawn to scale. There is just no correlation. Okay, so to answer that question, it means that there is no correlation between the measured length on the map to the actual length in real life. There is no correlation between the two. Good. Let's have a look at the next question. 2.3.3. Complete. Pretoria Hotel is at the corner of what and what street? So if you have a look at this map, we've already circled where Pretoria Hotel is. So now we need to determine it's at the corner of what and what street. So we can see that it's at the corner of Kloof Street and Albert Street. Do you see there? That's where Pretoria Hotel is. The corner of Kloof and Albert Street. Okay, remember we just want to complete the sentence. So it will be Kloof Street and Albert Street. Good. Question 2.3.4. State the probability of having a traffic light at Brooklyn Circle. So remember, even before we get started with calculating probability, let's just write down our formula. Probability is equal to what? Favorable outcomes divided by total outcomes. So what are the favorable outcomes? Based on this question, they are asking you to determine the probability of having a traffic light at Brooklyn Circle, right? So we need to determine where is Brooklyn Circle, okay? You'll see that this is where Brooklyn Circle is. It's there. So what's the probability of having a traffic light there? 0, okay? It's 0. There are no traffic lights there at Brooklyn Circle, okay? So the probability, okay, is favorable outcomes. Let's just use that. Favorable outcomes. Do we have any traffic lights there? 0. Divided by total outcomes. How many traffic lights are there on this map? There's a lot. There's like 4, 8, 12, 16, 20, 24. Let's count again. 4, 8, 12, 4, 8, 12, 16, 20, 24, 28, 32. I'm just doing this for the purpose of you understanding the concept. Please, 32, but 0 divided by 32 is still 0. So the probability is just 0. Okay, that is it. Question 2.3.5. Give one reason why some streets are numbered from 1 to 7. Why are some streets numbered from 1 to 7? So remember when we were basically looking at just analyzing this roadmap, I did mention that they are numbered from 1 to 7 because they are indicating the different routes that people can use to get to Pretoria Hotel. So question 2.3.5, okay, they are indicating the different routes that people can use to get to Pretoria Hotel. Good, right? And lastly, 2.3.6. 2.3.6, what is happening there? So we are told that a receptionist, right? a receptionist at the Pretoria Hotel has to report for work by 5:30. Okay, so she needs to be at work by 5:30 in the morning. That's incredibly early. She takes 10 minutes to walk from home to board a taxi. She leaves home at 04:55. She rides a taxi for 20 minutes and she walks 5 minutes from the taxi stop to the hotel. Verify whether or not the receptionist will get to work on time. So now, obviously, we're trying to verify if the receptionist is going to be at work by 5:30. We're not going to use that value in our calculation. We are trying to verify it. So it's not going to be in our calculation. So we're going to start off with the time that she leaves home. She's leaving home at 05:55. Then she walks for 5 minutes. So 05:55 plus 5 minutes puts us where? So if you plus 5 minutes, it puts us at 05:00. Then I'm going to plus 20 minutes. So if I plus 20 minutes, it puts us where? At 05:20. Then I'm going to take 10 minutes. Okay? So I'm going to plus 10 minutes and it's going to put us where? 05:30. So she is going to get to work on time based on these calculations. So I'm going to do it again. I started with the 5 minutes because it makes my life easy. 04.55. I mentioned that she's gonna plus 5 minutes. Okay. The 5 minutes is the 5 minutes that she walks from the taxi to the hotel. Okay. So it leaves us, if you plus 5 minutes, we're gonna be at 5:00. Then I'm gonna plus 20 minutes there. 20 minutes is the taxi ride. That's going to leave us at 05:20. Then I'm going to plus lastly the 10 minutes walk from home to board a taxi. Then that's going to leave us at 05:30. Therefore, we can conclude that what? The receptionist will get to work on time. Done. Right. And we are done with question number 2. Right. So now, up next is question number 3. So let's have a look at question number 3. Okay. It says Andrew and Duncan went fishing for carp on a friend's farm. Okay. Note, carp is a large freshwater fish that can be eaten by humans. Question 3.1.1. A female carp can lay 2.7 million eggs. Write 2.7 million in full using numerals only, right? So for this question, right, they just want us to write out 2.7 million using numbers only. Okay, so let's basically do that. So it's 3.1.1. If you have to write out 2.7 million in numbers, then we know it's going to be 2. It's 7. That 7 is already taking the space of one of those zeros for a million. Remember, if it's a million, okay, if you're given 2.7 million, right, we know that we're supposed to have 6 zeros, okay? If it was just 2 and million, we know that it was just going to be writing the 2 and writing 6 zeros. But in this case, this 7 is already taking up the space of one of those zeros. That is why we are just then going to write how many other zeros? 1, 2, 3, 4, 5. So it's going to be 1, 2, 3, 4, 5. So that's basically us writing 2.7 million as a number. Also, alternatively, another way that you can just do this, you can just take 2.7, you can multiply it by 1 million, okay, and that will also just still give you the same answer. Right, cool stuff. Let's have a look at the next question. Question 3.1.2. Andrew caught a carp with a mass of 2.375 kg. Duncan caught 2 carp, right? One weighing 1.2 kg and the other 750 grams. Determine in kg the total mass of the carp they caught, right? So here, right, we basically need to do a bit of conversion, okay? We need to first convert the 750 grams into kilograms. Then we want to add up all these masses together to determine the total mass of the cup that they caught, right? So how do we convert mass, right? So here, when you have to, do mass conversions, what diagram are you supposed to make use of? Okay, so for mass conversions, right, it's tons, kilograms, grams, milligrams. Okay, when you're moving from your bigger unit to a smaller unit of measurement, we know we're just supposed to multiply. So in this case, multiply by 1,000, multiply by 1,000 still, multiply by 1,000 still. And when you move from a smaller unit, excuse me guys, from a smaller unit to a bigger unit, you're going to divide by the value that you multiplied by. At the top, it's going to divide by 1,000, divide by 1,000. So in this case, we want to start off by just converting that 750 grams to kilograms. How do you convert grams to kilograms? So we are currently here. We want to go there. So what are we supposed to do? We are going to divide by 1,000. So if you divide by 1,000, how much do you get? You get 0.75 kilograms. Okay, now we are more than ready to then get the total mass of the cup. So the total mass of cup will be equal to 2.375 kg plus 1.2 kg plus 0.75 kg equals 4.325 kg. So that's now the total mass of the cup. So here, right, question 3 was just basically, us doing a bit of conversions. Okay, good. Let's have a look at question 3.2, right? Question 3.2 now deals with volume, deals with ratios. Okay, so you need to now pay close attention, right? And see how you're supposed to tackle this question. So Andrew wants to erect a vibrocrete wall on the boundary of his property. The wall will consist of concrete posts with precast concrete slabs between them. The wall will have 12 posts. Okay, the wall will have 12 posts planted into the ground using concrete. On top of each post, he will place a post cap. For each post, Andrew digs a square hole in the ground with a side length of 30 centimeters and a depth of 60 centimeters. Right? So just a quick analysis of what's happening here. All right? So they've given us a picture of the vibrocrete wall that Andrew wants to erect on his property. It's very important that we understand when they're talking about a post, they're talking about that rectangular part there. When they're talking about a post cap, they're talking about that part there that looks like a triangular shape at the top. And when they talk about the concrete slabs, they are talking about this there, what you slide into these posts. Okay, it's very important that we understand that. Right, question 3.2.1. Calculate in meters cubed the total capacity of all the holes dug for the required posts. So remember, we are told that Andrew wants to dig square holes into the ground. So we want to calculate what is the volume, how much can all of these holes hold. Okay, that's basically what you're trying to calculate. First thing that we first want to do, if we are told that the hole is a square hole, okay, so it's a square hole, that's the hole that he's now going to dig. Okay, try to visualize this in 3D. That's the square hole that he wants to dig onto into the ground. So if it's a square hole and we are told that the side length, okay, the length of one side is equal to 30 centimeters and the depth of this hole is 60 centimeters, what would be the volume of this hole? So because it's a square hole, it basically means that all the lengths of all the sides are the same. So to calculate the volume of the square hole, what will we do? Volume is equal to area of the base multiplied by height. We already also given the formula that we can use there, okay? Length times width times depth, okay? But area of the base times height. What is meant by area of the base? The base there is our square, right? How do you calculate area of a square? It's length times length times, instead of height there, sorry, it actually needs to be depth. Okay, so times depth. Okay, so therefore, the volume of this hole will be calculated using this formula. Okay, or you can just substitute it into this formula that's given to us, length times width times depth. Okay, we already know that it's a square, so also that other length width is just also going to be equal to 30 centimeters. Okay, potato. But we are told to calculate this volume in meters cubed. So that means that we first need to convert these dimensions that are given to us in centimeters into meters. How do we convert centimeters into meters? Okay, we are just going to divide by 100. Okay, if you want to convert from centimeters to meters, we are just going to divide by 100. Okay, so if you take that 30 centimeters, you divide by 100, we're going to get our answer. Divide by 100, we are going to get our answer. 60 divided by 100 is equal to 0.60 meters. 30 divided by 100 is 0.30 meters. Okay, so that means that also the width is just 0.30 meters. Now, length times length, it's 0.30 meters times 0.30 meters times, what's the depth? 0.60 meters. Punch this into your calculator. You will get that the volume of one of those holes is just 0.054 meters cubed. So this is the volume, okay, of one hole. That's how much concrete one hole can hold. But remember, he's not just going to be digging up one hole, okay? They wanted us to calculate the volume of all the holes, okay? What is the volume of all the holes required for the posts? So now we need to basically determine this. If he wants to basically put up 12 posts, how many holes will he need? Remember, he's putting up all these, posts around his property, right? So for me, to help me better understand what's happening here, if he's putting up these posts, he's putting up 12 posts. I just wanted to, draw the area of his property. This is basically his property, right? And he wants to, basically put up 12 posts, né? So if he wants to put up 12 posts, what does this mean? Maybe this is post number 1, another post 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you see I've put up posts around my property? So how many holes is he supposed to dig? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the total amount of holes that he wants to dig. So that basically means that from this volume that we've calculated, we just need to multiply it by 12, right? So then that multiplied by 12 means that the total capacity of all the holes required, okay, for the posts is equal to 0.648 meters cubed. Good. Question 3.2.2. Andrew mixed the same volume of concrete as the volume calculated in question 3.2.1. Give an explanation why he had some concrete left after planting all the posts in the holes with concrete. Why would Andrew have extra concrete left? Okay, because he actually, we found that he just needs exactly 0.648 meters cubed of concrete. Okay, but why does he have concrete left? Right? He can, to think of this, right? We can see that now. These are the holes that he's digging. These are the holes that he's basically, digging, right? Why would he have extra concrete left there? you can see that these posts also take up a bit of space there in the hole. They're taking up space there in the hole. So that's why then, because these posts are taking up space in the hole, you'll find that now they, occupying a bit of space there, right? Making the concrete that is required in that hole a bit less, okay? So that is why he still has a bit of concrete left there. Okay, so then to give our reason there, we can just say that those posts, okay, the posts are taking up space in the hole. Good. Last question. Question 3.2.3. The concrete is made from a mixture of cement, river sand, and stone in the ratio as listed below. You need 1 bag of cement, 2 wheelbarrows of river sand, 2 wheelbarrows of stone. Okay, we are told that 0.75 meters cubed of concrete requires 5.5 bags of cement. 1 level wheelbarrow full of river sand weighs 105 kilograms. So we are told that 1 level wheelbarrow weighs 102 kilograms. We want to calculate the mass of river sand needed to make 1 meter cubed. So now, how would we go about calculating the mass of river sand needed if we need 1 meter cubed of concrete? Okay, so with this question, right, we need to first, figure out where we need to start. Okay, what do we need to do, right? We are given the ratio there, okay? This ratio of 1 bag of cement gives us 2 wheelbarrows. 1 bag. To make concrete, we need 1 bag of cement, 2 wheelbarrows of river sand, and 2 wheelbarrows of stone. Let's write that down. To make concrete, we need 1 bag of cement, we need 2 wheelbarrows of river sand, and we need 2 wheelbarrows of stone. What else was given to us there? Okay, we are told that 0.75 meter cubed of concrete requires 5.5 bags of cement. Okay, we are told that 0.75 meters cubed of concrete requires 5.5 bags of cement. So now remember, from the question, we were told that we want to basically make how much? We want to make 1 meter cubed of concrete. So now, from the statement that is given to us there, right? From the statement that is given to us there, that 0.75 meters cubed of concrete is equal to 5.5 bags of cement, right? This is concrete. We want to now determine how can we make that 0.75 meter cubed of concrete into 1, because that is what we want to make. 1 meter cubed of concrete. So now to change the 0.75 meter cubed of concrete into 1, what you need to do, you just need to divide by 0.75. Divide by 0.75. What you do on the left, you need to do on the right. So 0.75. 0.75. When we divide by 0.75, when we divide by 0.75, we will then get how many bags of cement will we need? Because once we are able to determine how many bags of cement we will need, then we can now use this ratio. We can now use this ratio to determine how many wheelbarrows of river sand and stone we will need. Okay, let's take it step by step. So if you take 0.75 meters cubed divided by 0.75, okay, it's going to give us 1 meter cubed is equal to 5.5 divided by 0.75. What are we getting? 7.33 bags of cement. So you see now, it's becoming easy. Okay, 1 meter cubed of concrete needs us to have 7.33 it recurs bags of cement. So now once we have this, our life is now easy. We are just gonna make use of this ratio to help us determine how many wheelbarrows of river sand we need. So this ratio is just telling us it's 1:2:2. So if I need 1 1 bag of cement, that just means the wheelbarrows just needs to be double the cement. So in this case, if I need 7.33 bags of cement, because I've basically now determined, sorry guys, I've got flu. I've basically now determined I need 7.33 bags of cement. That's the cement. So I'm just relating now this to this. Okay, let me just do it like that. Remember, it's 1 cement, 2 wheelbarrow, 2 wheelbarrow. Cement, river, sand, wheelbarrow, stone, wheelbarrow. So we found that we actually need 7.33 bags of cement. So that just means to determine the river sand and the wheelbarrow, it will just be double based on this ratio that's given to us. Okay, we will use that ratio to help us determine the ratio, the new ratio. Okay, so then if it's 1, it becomes double. So if it's 7.33, we just need to double the 7.33. So 7.33 multiplied by 2 and 7.33 multiplied by 2, meaning that now, okay, it means that, okay, if we want to make 1 meter cubed of concrete, we're going to need 7.33 bags of cement. We are going to need 7.33 times 2, 14.66. This is bags. This is wheelbarrow of river sand, and 14.66 wheelbarrow of stone. Okay, now let's have a look at the question. Calculate the mass of the river sand that will be needed. They didn't ask how many wheelbarrows will be needed. All that we've calculated here, we've just found that, oh, okay, we are just going to need 14.66 wheelbarrows of river sand. But they don't want wheelbarrows. They want how many, the kilograms. Okay, right? So how can you convert wheelbarrows to kilograms? We were told that 1 level wheelbarrow is equal to 102 kgs. So that just means to convert these wheelbarrows into kgs, we're just going to take 14.66 wheelbarrows multiplied by what we want the kgs, divided by what you have, 1 wheelbarrow. Okay, answer 14.66 multiplied by 102, you'll get that you need 1495.32 kgs of river sand. Okay, we basically need that amount, right? Okay, and then remember here, because we actually dealing with real life situation, you can just round it off to the nearest whole number, which is approximately equal to 1496 kilograms of river sand. All right, so I hope you guys enjoyed this question here, right, where we just needed to now work with this ratio to help us answer this question here, right? Just to help us approach this question. First thing, look at the question. Okay, we want to make 1 meter cubed of concrete. So from the information that is given to us there, can we get an equation that we can work with that can help us, translate something that is telling us about concrete into 1 meter cubed of concrete is equal to something? Yes, it's this one. Okay, then from there we just now change that 0.75 meter cubed into 1. How can we change it into 1? Divided by 0.75 divided by 0.75 becomes easy now, because we've got 1 meter cube requires us to have something, bags of cement. So now once we have those bags of cement, our life becomes easy. We can just relate it using this ratio that was given to us there. Right, let's have a look at the next question. Question 3.3. The square-based post cap has a side length of 15.24 centimeters, okay, and a constant height of 2.5 centimeters. The perpendicular height of the triangular face is 7.86 centimeters as shown in the diagram alongside. So here we're just given the dimensions of that post cap, okay, that triangular part that we want to put there at the top, okay, and we're also given a net diagram, right? Okay, if we were to open up this post cap, how would it look? Okay, so we can see here that the concept that is being tested in question 3.3 is surface area. Surface area. Okay, now we are told that Andrew will paint two sides of each of the concrete posts, and we are told that each is 1.25 millimeters wide and 1.6 meters long, and the outside faces and all the outside faces of the post caps, right? The following formula may be used to calculate area of a rectangle, its length times width. Area of a triangle is half times base times perpendicular height. Right. So question 3.3.1 calculates in centimeters squared the total area of all the post sides that have to be painted. Right? So we're not going to forget what we've done in the previous question, right? We are just trying to determine what is the total area of the post. That's the post there. That's the posts, yeah, that have to be painted. Remember, we were told that it was 12 posts. He wants to paint 12 posts, right? And we were told that he only will paint two sides, right? Two sides of the concrete post, okay? And we're given the dimensions of the concrete post. So what are the dimensions of the concrete post? I'm just going to draw it here. So this is our concrete post. We were told that it's 1.25 millimeters wide and the length is 1.6 meters, right? So that's the length there, okay? That's the length. We are told that the length is equal to 1.6 meters, okay? And that's the width. We're told that the width is equal to 125 millimeters. We want to calculate the total area that has to be painted in centimeters squared. So the first thing that we want to do, we want to first convert the meters to centimeters, the millimeters to centimeters. How do we convert? You need to think back to that diagram. Okay, how will we convert this 1.6 meters sorry guys, to centimeters? So to move from meters to centimeters, we're going to multiply by 100. So 1.6 meters multiplied by 100 gives us 160 centimeters. So the length is 160 centimeters. What is the width? It's going to be 125 millimeters. So when you want to move from millimeters to centimeters, we are going to divide by 10. So it's going to be equal to 12.5 centimeters. So the width is 12.5 centimeters. So we want to calculate now what is the total area that has to be painted. So we are told that obviously he's going to be painting two sides of that. So it's that front side, right? And the back side, right? So let's just start with calculating the area of one side. So the area of one side or one face is going to be equal to, how do you calculate area of a rectangle? It's length times breadth. So what's the length? It's 160 centimeters. What's the breadth or the width? Sorry, length times breadth, length times width. Okay. What's the width? It's 12.5 centimeters. So 160 multiplied by 12.5 gives us 2,000 centimeters. Centimeters times centimeters squared. So that's just the area of one face. We were told that he wants to paint two sides of the concrete post. So then the area of two faces will be equal to that 2,000 centimeters squared times 2, which is going to be equal to 4,000 centimeters squared. We've calculated the area, the total area that has to be painted of just one post. But remember, he's not just painting one post. There are 12 posts that he's going to be painting. So then the total area of the posts will just be that 4,000 centimeters squared multiplied by 12, which is going to give us 24,000 centimeters squared. Sorry, it's not 24,000. I made a silly mistake there. So 4,000 multiplied by 12, this should give us 48,000 centimeters squared, right? So that's the total area of all the post sides that have to be painted, right? So we're basically done with question 3.3.1. Question 3.3.2. Duncan stated that the total area of all the posts and the post caps to be painted was 52,704 centimeters squared. So that's the total area that he's saying needs to be painted, rounded to the nearest whole number. Now we need to verify, showing all calculations, whether his statement is correct. So now, where do we start? He's saying that the total area of the posts and the post caps to be painted is that amount. So let's see. He's stating that, question 3.3.2, the total area of posts plus posts caps. He's saying that it's 52,704, right? So we want to verify if that is correct. So we're going to obviously use this approach. We've already calculated the total area of the posts that have to be painted. It's 48,000 centimeters squared. Plus, we just need to determine what is the area of the post caps that have to be painted. What is that total surface area? Okay, so then the surface area of the post caps, what must we do, is equal to what? Let's see. So we can see that the post caps, at the top, we've got triangles. We've got a triangle number 1 there, triangle number 2 there, triangle number 3 there, triangle number 4. We've got 4 triangles. So that means that we want to calculate the total areas of all of those 4 triangles and then add them up together. Then what else do we see? We've got rectangles there. 1 rectangle, 2 rectangle, 3 at the back, 4 rectangles. Okay, so you can also just make use of this net diagram to guide you when it comes to calculating, the total surface area of this post cap. So what do we need to do? We want to first start off by calculating what is the area of one triangle. How do we calculate the area of a triangle? It's given to us: half base times perpendicular height. What is the base of this triangle? It's 15.24. What is the perpendicular height? It must make a T for it to be a perpendicular height. It's 7.86. So we're going to start off by just calculating the area of just one triangle. Okay, so it's going to be, we're going to just say 4 times area of a triangle, because it's 4 triangles we counted, plus 4 times the area of the rectangle, because we did see that there's 4 rectangles there, right? 4 rectangles there as well that have to be painted. It's 1, it's 2, it's 3 at the back, it's 4. Also 1, it's 2, it's 3, it's 4. Hence the 4 times 4 times. Okay, then from there, what do we need to do? How do we calculate area of a triangle? Right, it's going to be 4 times half times base times perpendicular height plus 4 times, how do you calculate area of a rectangle? Length times breadth equals, then let's just substitute. It's going to be half. What's the base of that triangle? Remember, I just said it's 15.24 centimeters times, what is the height? We saw it is 7.86 centimeters plus, it's 4. What is the length of the rectangle? You can see there, the length of the rectangle there, it's this one, it's there, it's 15.24 centimeters times, what's the breadth? Let's see, we were given there. Do you see that? So the breadth is that, it's the height. So if this is the length, this is the height there, right? It's that breadth there, because we are just focusing on this shape there. So if this is the length, then this is our breadth of the height. Okay, so it's 2.5 centimeters. So now let's just punch these into our calculator. So it's going to be 4 times open bracket. It's going to be half times 15.2 times 7.86. What are we getting inside the brackets? It's 59.736 centimeters times centimeters squared, plus 4 open bracket, 15.24 multiplied by 2.5, you're getting 38.1 centimeters times centimeters squared. Therefore, 4 times 59.736 gives us 238.944 centimeters squared plus 4 times 38.1 gives us 152.4 centimeters squared, and then 238.944 plus 15 not 15 152.4 gives us 391.344 centimeters squared. So this is just the surface area sorry, of one post cap. But now for all of the posts that he's going to erect, he needs to put a post cap. So that just means that we need to still multiply that by 12. So we're going to multiply by 12. What are we getting when you multiply by 12? Okay, so I made a silly mistake here. Let's just correct it quickly. Okay, so if you take, it's going to be 4. It's going to be half times 15.2 centimeters times 7.86. It's going to be 59.8932. Let's just fix that. Plus, okay, 4 times, so it's just going to be 15.24 multiplied by 2.5. It's going to give us 38. Okay, it's going to be 4 times 38.1. Simplify further. 4 times 59.8932 gives us 239.5728. It's centimeters squared plus 4 times 38.1 gives us 152.4 centimeters squared. If you punch these values together, it's going to be 239.5728 plus 152.4 gives us 391.9728 centimeters squared. So this is just the surface area of one post, right? So remember, we want to basically, erect 12 posts, okay? And for every post, we've got a post cap. So we need to multiply that by 12. If you multiply by 12, what do you get? Okay, you get 4,703.6736 centimeters squared. Right? So then we're going to just substitute it now into that formula we had there at the top, right? That's the post caps, right? We got that it's 4,703.6736 centimeters squared, right? So therefore, the total area that needs to be painted is 48,000 plus 4703.6736. It's 52703.6736 centimeters squared. Let's just check and see if we've answered the question. Okay. Round it to the nearest whole number. So we want to round off this value to the nearest whole number. So if you round it off to the nearest whole number, we've got a 6 here. So this 6 is basically going to make that 3 what? A 4. So it's going to be approximately going to be 52704 centimeters squared. So we now can, we can confirm, right? We can confirm what? We can confirm that Duncan's statement was correct. Okay, we actually are going to be painting 52,704 centimeters squared. Okay, good stuff. Okay, so you just need to confirm and say that, therefore, his statement is correct or valid. Okay, let's have a look at the last question for question number 3. Okay, the spread rate of paint is 12.46 liters per meter squared. What does this mean? Remember, I've always just said this. If they give you a rate, write it as an equation, okay? If they're talking about the spread rate, they're just saying that, okay, for how many liters will you need to paint 1 meter cubed, right? Okay, so that's basically what we are told there. So we are told that the spread rate is 12.46 liters per meter squared. So that is just telling us that question 3.3.3, if the spread rate is 12.46 liters per meter squared, we can write this as an equation, right? 1 meter squared will paint, an area of 1 meter squared needs 12.46 liters of paint. That's it. Write it as an equation, because once you have it as an equation, it becomes a breeze. Life becomes a breeze, because whatever question that they can bring at you, you'll be ready for it. Let's see. Calculate how many liters of paint is needed to paint 52,704 centimeters squared, right? So if you want to paint 52,704 centimeters squared, how many liters of paint will you need? Easy. Using this equation, multiply by what you want, divide by what you have, right? What do we want? How many liters of paint? So you're gonna multiply it by 12.46 liters. Units are not the same. We've got centimeters squared, you've got meters squared. So now we need to first do something before we can apply this, right? What do we need to do? We can either change those centimeters squared into meters squared so that we can apply this equation properly. How do we convert centimeters squared to meters squared? Please take note of this amazing strategy, right? This is kilometers, meters, centimeters, millimeters, right? Okay, so still the same thing. We all know what's happening here. Nothing new, okay? Multiply by 1,000, 110. Divided by 10, 100, 1,000. But now, remember, we want to convert centimeters squared. We want to convert that's 52704 centimeters squared to be meter squared. So how do we do that? You're gonna square, 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 square. So if you're squaring those values, you need to also square there. Square, 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 square. Okay, what does this mean? To convert 52704 centimeters squared to meters squared, what are we going to do? We want to move from this one to that one. So according to this diagram, what are we supposed to do? We're going to divide not just by 100, but by 100 squared. Divide by 100 squared. So it's going to be 52704 divided by 100 all squared. Okay, then you'll get that it's actually 5.2704 meters squared. Now we can work with this now. We can work with this and take that value 5.2704 meters squared. Multiply it now by what we want. We want the liters, which is 12.46 liters divided by what you have, 1 meter squared. Do you see now the units will cancel properly nicely? Okay, our answer will be 5.2704 multiplied by 12.46 divided by 1. What do we get? Get your answer of 65.67 669184 liters. That's how many liters you'll need, which is approximately, okay, just round it up. It's a real life situation, 66 liters. Okay, we need approximately 66 liters of paint. All right, so we are basically going to stop it here now. I hope you guys enjoyed question 1 all the way up to question 3. The next question, we are going to be looking at question number 4. We are going to be analyzing a layout plan still there as well. So please make sure you just take a 2-minute break and then we are going to continue. Right, so let's have a look at question number 4. Right, it says a program inspiring people of all ages and genders usually ends with a fashion show, right? Annexure B shows the layout of the runways and the seating arrangements at the fashion show. Next to the floor runway are single seats arranged in rows. Each round table next to the raised runway can seat a maximum of 10 adults. Each of the runways is 4 feet wide. Okay, right. Note 1 meter is equal to 3.28084 feet. Use information above and annexure B to answer the questions that follow. So here, let's just see what's happening here. What is basically happening here? So we can see that here we're given like a layout, a plan of the runways and the seating arrangements at a fashion show. We can see that this is the 54. Then there's the inverted comma floor runway, and then here we've got the 24 raised runway. Then we've got the photographer, then obstructed view, keep area clear for photographer. So they're saying that people must keep this area clear for the photographer. We can see that there's a door here, there's a door here. Sorry, these are the single seats, right? And then we are told what that 54 with that inverted comma means. It basically means 54 feet. So this is a 54 feet floor runway. This is a 24 feet raised runway. Okay. And obviously these are the round tables, and that is also the door there. So let's see here. Question 4.1.1. They say write in simplified form the ratio of the width to the length of the raised runway. So let's have a look at the raised runway. What is the ratio of the width? Okay, so what is the ratio of the width to the length of the raised runway? So let's see here. All right, we are basically told that each runway is 4 feet wide. So what does that mean? It basically means that from there to there, each runway is 4 feet wide. So even with this one, it's 4 feet wide. So 4, that basically means feet. Okay, so then what would now be the ratio of the width to the length of the raised runway? So remember, ratio questions, it tells you exactly how you need to approach it, right? So question 4.1.1, ratio of the width to the length of the raised runway. So let's see, ratio of the width. So this is the raised runway. So obviously we are focusing our attention on this runway. What is the width? It's 4 feet. So it's 4 feet to, what is the length? 24 feet. Okay, right, sorry. So they want our ratio to be in simplified form. So remember, when they say simplified form, remember we need to have our final answer as a whole number. So I'm just going to divide that by 4 feet. Okay, divide that by 4 feet. Okay, so 4 feet divided by 4 feet is 1 is 2. How many times does 4 go into 24? 4 goes into 24 6 times. So it's 1 is to 6, and that is basically my final answer. Right, good. Question 4.1.2. Convert the length of the floor runway to meters. Right, so we want to convert the length of the floor runway to meters. So what's the floor runway? It's 54 feet. How can we convert these feet into meters? We are going to use this equation that's given to us there. Okay, we are told that 1 meter is equal to 3.28084 feet. Okay, meaning that if I want to convert 54 feet, what am I supposed to do? Multiply by what I want. I want to convert to meters. So I'm going to multiply by 1 meter divided by what I have. I have my units in feet. So I'm going to divide by 3.28084 feet. So if you punch this into your calculator, you'll see that the feet and the feet cancel. So 54 multiplied by 1 over 3.28084, you will get that 54 feet converted to meters is actually equal to 16.45919947 meters. Okay, and then we can just round it off to 2 decimal places. Can be 16.446 meters, right? So that's then our answer in meters. Question 4.1.3. Give a possible reason for each of the following, right? Why the second and third row seats are not arranged exactly behind the first row seats that are closest to the floor runway. So let's see the floor runway. What's happening here, right? Obviously, we want to determine why is it that, if you look at these seats, why is this seat not put directly behind that one? Why is that? Okay. Why are they arranged like this? It's kind of like moving, it's like slanting like that. Okay. Why is the second and the third row seats not arranged exactly behind? Why are they not exactly behind the first row seats? Okay, so the reasoning behind this, okay, based on what I think, is that they've arranged it like that so that the second row seaters, right, can see the stage properly without being without their view being obstructed by the first row seaters, right? Also, so that the third row seaters can see what's happening in the stage without their view being obstructed by the second row seaters. Okay, so to eliminate the obstruction that could be caused by the front row spectators or seaters. Okay, let's write that down. So question 4.1.3a, to eliminate obstruction that can be caused by first row seaters or spectators. Question B, why there is a gap between the two runways. Why is there a gap between these two runways? What is this gap for? So you can see that between these two runways, do you see that there's a gap there? What could that gap be for, right? So what I'm thinking there's probably a gap so that people can just move easily, all right? So it forms, as a passage, okay? It makes it easy for people to move around so that it can be easy for people to move around. B, so that it is easy for people to move around. Okay, it acts as, or it is a passage, not X. Okay, it is a passage. Good. Question 4.1.4, right? The diameter of the round table is 1.8288. So this is the round table here. All right, this is the round table. And we're told that the diameter, so the diameter is from the circumference to the circumference through the center, right? We are told that the diameter is equal to 1.8288 meters. You may use the following formula in the questions that follow, right? Area of a circle, circumference of a circle. Calculate the area of the top of one round table. Very easy here. If you want to calculate the area of a circle, right, or the top of this round table, what do we need to do, right? We are basically given the formula that we're supposed to use. Okay, it is area of a circle is equal to the pi 3.142 multiplied by radius squared, right? But here, remember, they didn't give us a radius for this table. They just gave us the diameter. So we just need to remember, then we need to then take that diameter of 1.8288 meters, and you're going to divide it by 2 all squared. Okay, so it's going to be, just going to simplify, so it's 3.142 multiplied by 1.8288 divided by 2 gives us 0.9144 all squared, meters all squared. Therefore, the area is 3.142 multiplied by 0.9144 all squared. Okay, it's 2.627 or 627 2165 meters squared. So that is the area of the top of one round table. B, each person occupies an equal length of the outer edge around the round table. Determine the maximum length allocated to each person seated around the round table. So remember here, we're given information that each round table can take a maximum of 10 people, right? So if it can take a maximum of 10 people, right, so let's just try to visualize. You can have 1, 2, 3, 4, 5, 6, 7, 8, 9, me try to fix it, make it bigger. Can take a maximum of 10 people, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what it means. Okay. Around this table, we can sit a maximum of 10 people. So now we want to determine what's the maximum length that one person is going to take up, right? So from there to there, what's that maximum length that one person can take up, right? So now in this case, if we're looking at around, because people are seated around this round table, it first means that we need to first calculate the circumference of this round table. Once we have the circumference of this round table, then, because the circumference is going to tell us what is the length around this table. Once we have the length around this table, we can just divide that by 10 to determine what's the maximum length that one person can take. Good. So let's first start off by calculating the circumference of this round table. So question 4.1.4b. How do you calculate the circumference? The circumference, okay, is equal to 3.142 multiplied by the diameter, right? We also know that we can also calculate the circumference by taking 2 times pi times r. Okay, but you can also still use this formula that's given to us there. So it's going to be 3.142 multiplied by, what's the diameter? 1.8288 meters, right? So if you punch this into your calculator, what's then the circumference or the length around our table? It is, okay, I'm getting that the circumference is, okay, I'm getting it's 5.746086 meters. So that's the circumference, right? But remember, we're just trying to then determine what's the maximum length that one person can, take up. Therefore, to get the maximum length allocated to one person, what are we going to do? We're just going to take this answer of 5.746086 meters, and we're just going to divide that by 10 because one table can take a maximum of 10 people. So if you divide by 10, what do we get? We can then see that the maximum length that is allocated to one person is 0.57460896 meters, which is approximately 0.57 meters. That's the maximum length that is allocated to one person. Cool stuff, right? Let's have a look at question 4.2. Question 4.2. Right, so question 4.2 deals with BMI. I hope you guys have watched my revision tutorials for paper 2. We have gone through calculating a line scale, bar scale, number scale, BMI, surface area, volume, everything. Okay, please make sure that you've gone through those video tutorials. Okay, it says that the girls participating in the fashion show need dresses that fit well. Okay, the fashion show uses an equal number of girls for each size. Okay, an extra C shows a body type chart used to select the correct dress size. Okay, so let's see what is happening here. So here we are basically given a body type chart used to select dress size. We can see that on your horizontal we've got the mass here, and then on your vertical we've got the height, and then here we are given the various body sizes. Okay, then we're given the dress size here, then here we're given the body size, right? Let's see if we can now use this chart to answer questions. Use an extra C and then information above to answer the questions that follow. Write down the body size. Write down the body size for a girl with a mass of 55 kg and a height of 1.6 meters. So if you have a mass of 55 kg, so that means that you're focusing here, 55 kg and a height of 1.6 meters, what is your body size? So we just need to find where is the intersection. So do you see that it intersects at extra small? So then the body size is extra small. Good. Question 4.2.2. State the mass of a girl with a height of 1.75 meters, wearing size 14 to 16. We are trying to determine what would be the mass of a girl that has a height of 1.75. So a girl has a height of 1.75. So let's see, height of 1.75. So it just means that we are somewhere here, right? Just somewhere here. We don't know yet, but we just know that we are here, right? And wearing a dress size of 14 to 16. So if they're wearing a dress size of 14 to 16, that means that we are here, right? So we need to basically see where is there a large, right? Where is there a large? So on, the height of 1.75. Do you see that there? So what would then be the mass of a girl? It would be 80 kg. It would be 80 kilograms. Good. Question 4.2.3. Calculate the body mass index of a girl who weighs 70 kg and is 1.5 meters tall. Very easy here. We know how to calculate BMI. Also, they've given us the formula that you're supposed to use. BMI is equal to mass of the girl, which is 70 kilograms, divided by the height of the girl in meters all squared. So what's the height of a girl? It's that 1.50 meters all squared. What are we getting as the BMI? So it's 70 divided by 1.5, so open brackets 1.5, 0 close bracket all squared. We are getting 31.11 kilograms per meter squared. So that is the BMI. Okay, good. Question 4.2.4. Write as a percentage the probability of random selecting a girl who weighs 50 kg and wears an extra small dress. So what is probability? We know probability is equal to favorable outcomes divided by total outcomes, right? So the favorable outcomes, we want to look for a girl who weighs 50 kg and weighs extra small, right? So we're going to look at what 50 kgs. That's 50 kg, weighs 50 kg there, and weighs extra small. Okay, what do we see here? It's 100%. Okay, 100%, because all of those rows basically have extra small. So the probability in this case will just be 100%, or it would be 6 out of 6. Why am I saying this? Because when you look at the different body sizes, we have extra small, then we have small, then we have medium. Okay, extra small, then small, then medium, then large, then extra large, then double XL, right? So how many categories do we have there for the body size? 1, 2, 3, 4, 5, 6. So the total outcomes is 6. What are the favorable outcomes? 1, 2, 3, 4, 5, 6. So what will be the probability? It's 1, or we can just say 100%. Good. Question 4.2.5. Bonello stated, okay. Oh, actually they said as a percentage, okay. So 6 divided by 6 times it by 100 is 100. Okay. 6 divided by 6 times it by 100. 6 divided by 6 is 1. Times it by 100 is equal to 100%. Okay, because they wanted it as a percentage. Question 4.2.5. Bonello stated that the probability of randomly selecting a girl wearing a dress with body size smaller than XXL is 0.833. Verify showing calculations whether her statement is correct. So now that basically means that we want to actually calculate what is the probability of selecting a girl that wears a dress size that is smaller than XXL. So then again, probability, favorable outcomes divided by total outcome. Okay. What are the favorable outcomes? We want to count all the sizes that are smaller than XXL. Okay. So how many? It's 1, 2, 3, 4. It's 5 sizes that are smaller than XXL. Divided by total outcomes is 6. How much do you get? 5 divided by 6. We get 0.833 recurs. Okay. Therefore, what can we confirm? We can confirm that the probability of randomly selecting a girl that wears a dress with body size smaller than XXL is true. Therefore, Bonolo's statement is valid. Okay, is correct. All right. So we are almost there, guys. I hope you guys enjoyed, this. I think the key here was just understanding that there was just 6 different dress sizes. Okay. And once you understand that, then it becomes easy for us to calculate the probability because we are able to identify the variable outcomes and obviously we know what the total outcome is, which is 6. All right. Now, we're going to be looking at the last question now. Question number 5. Question number 5 deals with surface area, it deals with volume, and it deals with us, converting from imperial system to metric system and also converting time. So please make sure that here as well, just take a 10-minute break, pause it, okay, then come back so that we can now finish off this past paper. Right, so we are almost there, right? We're going to be looking at the last question. Question 5, right? So question 5 deals with, calculating surface area, volume, converting from from imperial to matrix system, right? So please, right, I'm going to reiterate this. If you haven't watched my revision lessons for paper 2, please make sure that you watch those revision lessons. They are really going to open up your mind on what you need to do when you're answering, these types of questions, right? So let's look at question 5.1. So question 5.1 basically says that ice is usually used in cool drinks to further cool them. Ice can be made by freezing water in different shapes, okay? Cubes are the most common shape used to make ice. So we're given a picture of, an ice cube and diagram of an ice cube, right? And then we are told that the side length of the cube is equal to 4.5 centimeters. Use the information above to answer the questions that follow. Determine the surface area of the cube, and you may use the formula, right? Calculating surface area of a cube is the easiest thing you could ever do. Okay, because we know when we're calculating surface area, what are we doing? We are just trying to get what is the areas of all the faces of the cube, and we want to add them all up together. So we want to find the area of the top, bottom, front, back, left side of the cube. Then we want to add up all those areas. Okay, but what do we know about a cube? What do we know about all the faces of a cube? They have the same area. Okay, because all the sides of a cube are equal. So what do we know then? To calculate the surface area of a cube, right? They've just simplified our life for us there. Question 5.1.5.1, to calculate the surface area of a cube is going to be 6 multiplied by length squared, okay, or side length squared. I'm going to say length squared. So then it's going to be 6 multiplied by, what's the length of one side? It's 4.5 centimeters all squared. If you punch this into your calculator, what do you get? 6 times 4.5 centimeters all squared. It's 121.5 centimeters squared. We are calculating surface area, emphasis on area. Therefore, the unit of measurement is centimeters squared in this context. Okay, good. Let's have a look at question 5.2. Countries surrounding the North Pole have started building ice hotels for travelers to stay overnight. The hotel buildings with furniture and decorations are made of big blocks of ice, each weighing 2 tons. Okay, so this is very important information here that these big blocks of ice weigh 2 tons. Blocks of ice are stacked on top of each other to build a room. Ice can also be carved to form shapes. Okay, so what's very important here that I can already see is that we can see that one block of ice. Okay, one block of ice. This is question 5.2. So one block weighs 2 tons. Okay, I'm just gonna put it there for future reference. Use the information above to answer the questions that follow. Question 5.2.1. Calculate the total mass in kg of a wall built with 60 big blocks of ice. Okay, so now if a wall is built with 60 big blocks of ice, what is this mass in kgs? Okay, so we've got 60 blocks and we want to convert this to kg. What do we need to do? Already we were told that one block weighs 2 tons. Okay, so I'm first going to convert these blocks to tons, and once I've converted these blocks to tons, I'm going to convert the tons to kilograms. Okay, so how am I going to do that? Very easy. How do you convert from blocks to tons? Because we've got an equation that's been given to us to use, multiply by what you want, divide by what you have. I promise you, it works every single time. If you've got an equation and you have to convert, it works every single time. So here, 60 blocks, multiply by what we want. In this case, I want to first convert to tons, because once I have it in tons, I can convert it to kilograms. So I'm going to multiply it by 2 tons divided by 1 block. Okay, so 60 multiplied by 2, this is going to just give us, okay, 120 tons. And then once we have it in tons, we can then use that other equation that's given to us. 1 kilogram is equal to 0.001 ton. Or you can also use that one, those strategies. Remember that I drew for you how we can move from a ton to kilograms, multiply by 1,000. Okay, or we can use this that's provided for us here. Please note, they don't provide all the time. Okay, so you need to now start training your mind to remembering, these things off by heart, right? So this is the second equation that's given to us. Let's say, for example, we've forgotten. Okay, then 120 tons, we're converting to kilograms. Multiply what you want, divided by what you have. Obviously, the other value there, 0.001 ton. What do you get as your answer? 120,000 kgs. Okay, so we have converted the 60 big blocks of ice into kgs. Cool stuff. Question 5.2.2. A block of ice was carved out to make a circular opening. The carved out ice was melted, resulting in water with a volume of 38,500 centimeters cubed. Calculate the volume of the ice that was carved out. You may use this formula. This question is nice and easy. Okay, nice and easy. We are given everything that we need. We don't have to be panicking, right? What do I mean by this? We are given that we use this formula. Volume is equal to, or volume of water actually. Volume of water is equal to volume of ice multiplied by 0.92. You want to calculate what is the volume of the ice. What's the volume of the ice that was carved out? Okay. What are we given? We're given the volume of the water. Water with a volume of, okay? So we're given this volume of water there. So just substitute, okay? Just substitute 38,500 centimeters cubed is equal to volume of ice multiplied by 0.92. Then what do we need to do? We are trying to solve for volume of ice. So that means that we want to isolate volume of ice. How do we isolate it? By getting rid of that 0.92. How do we get rid of 0.92? By doing the inverse of multiplication, which is division, 0.92, 0.92. Therefore, volume of ice is equal to 38,500 divided by 0.92 gives us 41847, comma. I'm going to just round it off to 2 decimal places, 83 centimeters cubed. So that is the volume of the ice that was carved out. Nice and easy. We were given everything there. All that we needed to do, just substitute into the formula and we're good to go. Right, last question. Question 5.3. Alaska is one of, the states in, let me try to zoom it in a bit. Okay. Alaska is one of the states in the USA, United States of America. Anchorage is the largest city in Alaska. An extra D shows a part of the globe indicating the shortest distances in nautical miles between Anchorage and a few selected cities in the world. Note, 1 nautical mile is equal to 1.15 miles. 1 kilometer is equal to 0.6215 miles. Use an extra D and the information above to answer the questions that follow. So let's have a look at what is happening here on an extra D. So this is the part of the globe indicating the shortest distances in nautical miles between Anchorage and a few selected cities in the world. Let's try to see, understand what's happening here, right? So what does this mean? Excuse me. What is the shortest distance between Tokyo and Honolulu? It's that value. What's the shortest distance between Moscow and Anchorage? It's actually Anchorage. Okay. Moscow and Anchorage, 3,800. What's the shortest distance between Berlin and that point there? Anchorage, 3,950, right? Shortest distance between Anchorage and Washington, 2,900. Okay, so that's basically how we are going to, go about working with this picture, right? So let's see. Question 5.3.1 says determine in nautical miles the difference in the distances from Tokyo to Honolulu and from Washington to Anchorage. So we want to first see what is the difference. What's the distance from Tokyo to Honolulu, right? So from Tokyo, where's Tokyo? This is Tokyo. Where's Honolulu? It's there. So what's the distance there? It's 3,350. 3,350. Then from Washington to Anchorage, Washington is here, Anchorage is here. What's the distance? 2,900. All that we want to do, we want to determine the difference in these distances, right? So to get the difference, question 5.3.1, the difference will just be equal to 3,350 nautical miles minus 2,900, okay? And you will get 450 nautical miles. Okay, question 5.3.2, convert 2 kilometers, the distance from Berlin to Anchorage. So what's the distance from Berlin to Anchorage? So where's Berlin? That's there. Where's Anchorage? It's there. What's the distance there? It's 3,950 nautical miles. 3,950. So it's 3,950 nautical miles. And we are asked to basically convert this, right? We have to convert this into kilometers. How can we convert nautical miles into kilometers? Remember, we are given these two equations that we can use here to help us when we want to convert, right? Okay, right? How are we supposed to now go about converting? The tip here is that we first need to convert these nautical miles to miles. Once it is in miles, then we convert those miles to kilometers. Okay, so listen carefully. So when I take 3,950 nautical miles, okay, which equation are we going to start off with? We're going to start off with the one at the top, this one. That 1 nautical mile is equal to 1.15 miles. Okay, multiply by, what do we want? I want to first convert to miles. So I'm going to multiply by what I want, which is 1.151 miles divided by what I have. Okay, 1 nautical miles. Okay, what do we get? Do you see that the nautical miles cancel? Whatever answer I will get, it will be in miles. So 3,950 multiplied by 1.151 divided by 1. What do we get? We get 4,546,45 miles. Once we've converted into miles, then now we are going to use the other equation to convert these miles into kilometers. Okay, so we've got now 4546, 45 miles multiplied by, what do you want? We want to move to now kilometers. So I'm going to multiply by 1 kilometer divided by what I have. I've got my units in miles. I'm going to divide by 0.6215 miles. Okay, what do we see? Miles cancel. 4546. Okay, sorry. 4546, 45 multiplied by 1 divided by 0.6215. What do we get? You get that your answer is 7315,29 kilometers. I'm just going to keep it, at like 2 decimal places. Okay, that's now our final answer in kilometers, right? Cool stuff. Let's have a look at the next question. Question 5.3.3, right? It says that cargo needs to be shipped from Los Angeles to Honolulu and then from Honolulu to Tokyo. Peño searched the internet to determine how long it would take the cargo to reach its destination. Shown below are the search results. Some information has been omitted, right? Then we are basically given, if you're going from Los Angeles to Honolulu, it takes 10 days and the distance is 2,607 nautical miles. If you're moving from Honolulu to Tokyo, we do not know what the time is, but that's the distance, 3,350 nautical miles. And then we are also told to note that a ship sail 24 hours a day, right? Now we need to calculate the average speed of this ship, rounded to 2 decimal places. Now in this case, they are telling us exactly how we need to round off, right? And they're asking us to calculate this average speed in nautical miles per hour. Okay, how do we calculate average speed? Yes, they've given us this formula, but how can we manipulate this formula to give us what we want? So this is question 5.3.3. How do you manipulate this formula? Please just remember, we can just draw this triangle, right? I've discussed this as well in my revision lessons. Okay, draw this triangle. We've got speed multiplied by time, right? So we know that if we are multiplying, they're just next to each other. This is my speed, this is my time. And then obviously the distance is going to be at the top. So that means that if value at the top, value at the bottom, we divide. Values next to each other, we multiply. They're asking us to calculate what? The average speed of this ship. How do we calculate average speed? Based on what we can see that now, we can see that to calculate average speed, okay, average speed is equal to distance over time. We want to calculate what? The average speed of the ship, okay? So we can see that we're going to obviously use time, this time that's given to us there, and this distance that is given to us there, okay? And they want the average speed in nautical miles per hour, okay? So the distance is already in nautical miles, so that's fine, but the time is in days and hours, okay? So that already tells us that we need to convert our time. We need to convert our time so that it's not just in days and hours, but just in hours. So how can we convert that? We know that one day, how many hours do you have in one day? 24 hours. So I want to convert these 10 days to be hours. So I've got 10 days. What must I do? I've got an equation that I've created for myself. So all that I need to do, multiply by what I want, divided by what we have. So I'm going to multiply. I want to convert to hours. So I'm going to multiply by 24 hours divided by what we have. Obviously, divide by the other value there. Okay, so we're going to get 240 hours. Okay, meaning that if I've got 10 days plus 4 hours, the 10 days is 240 hours plus 4 hours, meaning how many total hours do I have? 244 hours. Done. So now I'm going to just substitute that into my formula. What's my distance? 2,607 divided by, what's my time? 244 hours. Okay, the distance is in nautical miles. Punch into your calculator. 2607 divided by 244. What are we getting? We are getting 10.68. We're going to round it off to 2 decimal places. Nautical miles per hour. Done. Last question. This is A. Last question finally. Even our throats are dry at this point. B. Hence determine the date and time of arrival in Tokyo. If the ship leaves Honolulu on the 24th of September at 1600 and sails at the same average speed. So now here we're just trying to determine what time and the date will we arrive in Tokyo. Okay, so we are told that the ship leaves. Okay, just gonna write it there. It leaves on the 24th of September at 1600. Okay, that's the time that this ship leaves. This is going to be very important when it comes to giving us our answer. But the first thing we need to do first, right, is calculate what is the time, how long, is this ship traveling, okay? Because we are told that it's traveling at the same average speed. We're going to use the speed that we calculated there, divided by, the speed and the distance. So if you've got speed, you've got distance, what can you calculate? The time that it will take, okay? So then we are calculating time. So we can just see here, I'm going to just do it in blue, green. Let me do it in white. We're trying to calculate time. So time is going to be distance in nautical miles divided by what? Average speed, okay? What's the distance? Okay, the distance is 3,350 nautical miles divided by what's the average speed? 10.68 nautical miles here. Here is nautical miles per hour, meaning that whatever answer that we're going to get when you divide these two values, it's going to be in hours. So 3350 divided by 10.68, what do you get? 313.670412 hours. So that's how long it's gonna take, okay, to travel from Honolulu to Tokyo. But now we want to determine then, right, if we're leaving on the 24th of September, when will we arrive? When will we get to our destination? So already there, we need to now first convert these hours into days and hours if we have to, and minutes. So let's see, right? How can you convert hours into days? What are we going to do? We know that 1 day is equal to 24 hours. So then from here, I'm just going to take that 313.670412 hours. I want to convert this to days. So I'm going to just multiply by what I want. 1 day. I want to convert to days divided by what we have. I've got hours. I'm going to divide obviously by the other value, hours. So then I'm going to multiply by what I want, divide by what you have. What are we getting? We are actually getting, it's what? 13.0696005 days. So this is actually equal to 13 days plus 0.0696005 days. So obviously this value, we can just convert it into hours, right? So then I can just convert that into hours. So this is 13 because it's a full day. We can just leave it like that. But this one, because it's a decimal, let's just change it to hours again. Okay, so I'm going to plus. How can we convert these days into hours? The same thing, 0.0696005 days multiply by what you want, 24 hours divided by 1 day, okay? Sorry. So it's going to be 13 days plus. So it's going to be that 0.0696005 multiplied by 24 over 1. It's just 1 hour, 0.6704048 hours. We can then also change these hours into hours and minutes. Okay, but I'm just going to stop there. Okay, I'm just going to stop there. So it's 13 days plus 1.67 hours. That's how long it's going to take us. So now we know from the 24th of September, we want to count 13 days. Okay, what's important here, we need to determine what is the last day of September. Is it the 31st? Is it the 30th? I always use my knuckles, right? So January, February, March, April, May, June, July, August, September. If it lands at the lower part, it means that the month is ending on the 30th. If it ends at the top part, it means that the month is ending on the 31st. So because we landed there, it means that September is ending on the 30th. The last day of the month for September, right, is the 30th. Okay, right? So how many days do we have from the 24th to the 30th? Okay, so it's 24th, 25, 26, 27, 28, 29, 30. So it's 6 days. Okay, plus that takes us to the 30th of September. Plus, obviously, how many more days do we have left? Remember, we're supposed to travel 13 days. We've only traveled 6. So 13 minus 6 gives us 7. So that means that now the rest for the 7 days is going to take us to 7th of October. Okay, because the last day from the 24th, let's actually write it like this so that you guys can see what's happening. Okay, from the 24th of September to the 30th of September, it's 6 days. Excuse me, 6 days, right? Then how many more days do we still need to travel? We just take 13 minus 6. We still need to travel 7 days. So for that 7 days, so from the 30th to the 7th of October is 7 days. So that means that we've traveled then a total of 13 days. Okay, so that means that when will be our destination? The date of arrival. So therefore the date of arrival will be the 7th of October. Okay, at 4, because remember we are leaving at 4, right? It's a full 24 hours. Okay, when we're counting, so it's going to be 7th of October at 4. Okay, at 4, but remember we still need to add 1 hour 0.67 hours or 1.67 hours. So that means that if we're adding 1 hour to that, if we plus 1 hour, okay, plus 0.67 hours, what does this mean? The 1 hour puts us at 1700, and then we just need to convert these 0.67 hours into minutes. How can we convert that into minutes? Okay, we are just going to take 0.67 hours. What do we know? Sorry guys, everything is 1 hour is equal to 60 minutes. Okay, so we're just going to take that 0.67 hours multiplied by 60 minutes, because that's what we want, divided by 1, because I just want to determine the minute. Okay, so 0.67 multiplied by 60 divided by 1, it's giving me 40.2 minutes. Okay, so that means that I'm gonna get there at 1700, okay, plus okay, 40.2 minutes. So that's approximately, let's just say the arrival time, let me just conclude, it'll be the 7th of October, 1740, approximately 1740. I'm just going to stop there because I'm not going to now find out how, what's this 002. I'm tired. Okay, so that's basically that. Okay, so I think we've handled this paper well, right? We can officially say that we're done with this. Okay, so please take note that, right? Make sure that before can say that, okay, I'm done, make sure that you've looked at the revision lessons, because that's what's important, that we go through these revision lessons first, so that we just get a general, a good, not even a general, tips on what we need to do when we are preparing for this exam. So please make sure that you have a look at these revision lessons, right? And all the best, guys, for your final paper there on Monday. And yeah, that is it. I'm gonna close it here.
That is it, guys, and I'll see you guys on my next upload, Distance Learning with Lee, where I make learning mathematics super easy. Bye, guys.